Okay, so in this video I'm going to have a look at limits of sequences. So what is a limit? A limit is some number, let's call it L, such that Tn, the nth term of a particular sequence, gets closer and closer to that value for larger and larger values of n. So for example, if we take the sequence 1, half, quarter, 1/8, 1/16, and so on. We keep going on forever into infinity. So this is term 1, term 2, term 3, term 4, term 5. If we keep going on to term, let's say, infinity, what number will this be out here? What number will this sequence approach? Well, we can see that it's eventually going to approach 0. The fractions here are getting smaller and smaller and smaller because the denominator is doubling each time, or we're halving each term. We're multiplying by a half each term. So this sequence approaches 0, and because this particular sequence does approach a limit, it's said to be convergent. It does approach a limit, so it's convergent. Now if we take another sequence, for example 1, 2, 4, 8, 16, and so on, in this particular case what's happening is our numbers are doubling each time, so we're multiplying by 2, and the numbers are getting bigger and bigger and bigger. This particular sequence will not approach any particular limit, so this is said to be divergent. Okay, so let's look at some properties of limits. So if we take the limit of, let's say, two functions f of x, and we'll add it to another function g of x, what's the limit of this here as let's say x approaches some number, I don't know, let's say a. So what you can do here is just get the limit as x approaches a of f of x and add it to the limit of g of x as x approaches a. So this is very simple. It looks a little bit more complicated than it is, in fact. So for example, if you have the limit of, let's say, 3x squared plus 4x. So this is my f of x, if you like, and this is my g of x. So that's just simply the limit of 3x squared plus the limit of 4x. So that's all you're doing there, really. So that's the addition of the sum property of limits. There's also the product property, so you can work out the limit, let's say, as x approaches a of f of x multiplied by g of x. So you can have two functions multiplied. For example, that could be multiplied instead of added. So that's just, again, simply the limit as x approaches a of f of x multiplied by all of this here, multiplied by the limit of g of x as x approaches a. So you just multiply the two limits, find the limits, and then multiply them. You've also got the quotient property. So again, if you have two functions divided, so if you have x approaching a again, and you've got f of x here divided by g of x, something like this, you just get the limit of the numerator. So you get the limit of f of x as x approaches a divided by the limit of g of x as x approaches a. So that would be something like, I don't know, 3x squared over 2x, something like that. So this would be your f of x, this would be a g of x. Get the limit of the top and the limit of the bottom. Okay, and the last one I'm going to look at is the root property. So if you have the limit, if you have the limit of, let's say, as x approaches a again, some number a, and you get the square root of some function, let's say f of x again, that's just simply the same as the square root of the limit of the function as x approaches a. So you just take the square root symbol here and get the square root of the entire limit, get the limit of the function, in other words, and then get the square root of whatever you get. Okay, so let's have a look at some examples of how you work out these limits. Let's take the root property. Or no, actually, I'll do an easier one first. Let's take this one here. Let's take the limit, and we will take n going out to infinity in this case of 3n minus n squared all over n squared plus 2n, n squared plus 2n. So we want to find the limit of this sequence as n approaches infinity. Now you might think, well, if I put infinity in here, 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 and here, really what I'll end up with is infinity over infinity, if you like, which is, I suppose, effectively 1. But that's really a nonsensical limit and incorrect, in fact. And I'll show you that in a few minutes. But what you need to do here is just rewrite this limit. So what you look at here is this n squared, and n here. And you can see that the highest power of n here is n squared. So what I'm going to do is take the limit here, n going to infinity, and I'm going to divide above and below by n squared, the highest power of n. So I'm going to divide each particular term here by n squared. So it won't change the fraction, if you like. It'll change how it looks, but it's still exactly the same fraction. So let's divide this by n squared. So that will be 3n over n squared minus n squared over n squared. And then on the bottom here we've got n squared over n squared. And here we've got 2n over n squared. So this is exactly the same fraction as this here. All we've done is divided above and below by n squared. So what does that give us? That'll give us the limit as n approaches infinity of 3n over n squared is just going to be 3 over n. Now n squared over n squared is just going to be 1, and n squared over n squared here is just going to be 1, and this is going to be 2 over n. Okay, so now we've got to find the limit of this thing here rather than this here. It's a little bit easier to do this one. You'll see that in a second. Now, one thing I should say here is that when you're finding the limit, first of all, of a quotient, using the quotient property, you get the limit of the top divided by the limit of the bottom. And when you get the limit of these two things here, which are added, or in this case subtracted, which is effectively the same thing, I guess, you're adding a negative, but you get the limit of this and the limit of this. And the same on the bottom. So what we're effectively going to do is find the limit of this, the limit of this, the limit of this, and the limit of this. So we're going to write this fraction down again just as limits. So if you take, for example, 3 over n, we'll just do this once here. If you take 3 over n, okay, and you look at the limit of this particular fraction here. Now remember, n is going out to infinity. N is getting bigger and bigger and bigger. So what's happening to the entire fraction? It must be getting smaller and smaller and smaller. So for example, if n was 1, we'd get 3 over 1, which is 3. If n is 2, we'd get 3 over 2, which is 1.5. If n is 3, we will get 3 over 3, which is 1. So here we have 3, 1.5, 1. If 3 was 4, we'd get 3 over 4, which is 3/4. So now we're out to 3 over 4. Then 3 over 5, and so on. 3 over 5 here. So you can see what's happening to our actual fraction here. We went from 3 to 1.5 to 1 to 3/4 to 3/5. It's getting smaller and smaller and smaller, and eventually it will approach 0. So the limit of 3 over n, as n gets bigger and bigger and bigger, as n approaches infinity, will be 0. The limit of this here will be 0. So this here will be 0, and you'll find that with any fraction where you've got an n on the bottom, or an n squared on the bottom, or an n cubed, or whatever on the bottom, that the limit of that particular fraction will be 0. So this here, the limit of this here will be 0. The limit of minus 1 is just going to be minus 1, because it doesn't change. Minus 1 is a constant, it's not going to change. The limit of 1 as n approaches 0, as n approaches infinity, is 1 as well, because n doesn't affect 1. Now here's another fraction with n on the bottom here. So as n approaches infinity, as n gets bigger and bigger and bigger, 2 over n is going to get smaller and smaller and smaller, and eventually it will approach 0. So the limit of 2 over n as n approaches infinity is just simply 0. So the limit of this here, the limit of this fraction here, is just going to be minus 1 over 1, which is just minus 1, as n approaches infinity. So what does that mean exactly? Well, remember that n is getting bigger and bigger and bigger. So this fraction here will approach minus 1. If we look at that from a graphical point of view, let's take, let's see, where do I have this? This here. This is a function here. Now instead of the n, I put in x's here. So it's 3x minus x squared over x squared plus 2x instead of the n's. And I've drawn that function here, and you can see it. It's here, it comes down along here, goes along here like this, and it's also along here and comes down along here like this. So if you were to plot this particular function here, this is what you would get. Now you can see here as well that you've got these two dotted lines along here. They're called asymptotes, and they represent parts of the graph or parts on our plane here where the graph doesn't actually reach. So you can see our graph goes up along here like this and continues on, gets closer and closer to our vertical asymptote, but will never actually reach it. And the same on the horizontal here. Our graph will come down along here like this, keep getting lower and lower and lower on into infinity, but never actually reach this line here, this asymptote, this horizontal asymptote here. Same in the negative direction here. It will come up along here like this, but never actually reach this. And look at this. This is the one we're interested in here, this horizontal asymptote here. Look where it goes through. It goes through minus 1, which is, remember, the limit. It's the limit of this function as n approaches infinity, or in this case x approaches infinity. I've changed the n's to x's. So as x approaches infinity, our function approaches minus 1, and we can see that that's the case. If we go out along the x-axis here, out into infinity, so we're going to go off out here to the right towards infinity, what happens to our graph? It gets closer and closer and closer to minus 1, but we'll never actually reach it. It'll approach minus 1, in other words. So the limit of our function as x goes out into infinity is minus 1. Okay, so that's effectively what our limit means, graphically anyway. Now our horizontal asymptote here, by the way, I'll just run through that. It's not really to do with limits but as such, but it's effectively where our graph here will approach minus 2. Okay, our graph will approach minus 2 but never actually reach it. And where did we get minus 2 from? Well, if you look at our function here, 3x minus x squared over x squared plus 2, if our denominator was 0, then this function wouldn't exist. So if x squared plus 2x was 0, our function wouldn't exist, and that's where we get this here from. So if x was a certain value, x squared plus 2x will be 0. Now what value is this? And you probably guessed that if x was minus 2, if we put minus 2 in here, we'll get 4. Put minus 2 in here, we get minus 4. So 4 minus 4 is 0. So here the denominator will be 0. The denominator will be 0 when x is minus 2. So we can't divide by 0, so this function doesn't exist at x is equal to minus 2. So that's how you would determine your vertical asymptote, if you like. You would take whatever's on the bottom here, whatever the denominator is, let it equal to 0, and then work out what x would be. So for example, if I go back here, our denominator was, what was it? N squared plus 2n, n squared plus 2n, or we'll say x squared plus 2n. If that was 0, if we let that be 0, what would x be? Well, you can just factorize it and you get x plus 2. So x is 0. So obviously if x was, so that means effectively that x is equal to 0 or x is equal to minus 2. Now, if x was 0, we can see that you would end up with 0 plus 0, so we would end up with 0 on the bottom. But what I'm looking at here is x is equal to minus 2. If x was equal to minus 2, our denominator here, x is equal to minus 2. Here's x is equal to minus 2, this line here, this vertical asymptote. If x is equal to minus 2, our denominator will be 0, so this function will not exist. It can't exist because you can't divide by 0. Okay, so let's just do one other example of a limit. And we're going to take the limit of, let's say, the square root of 4n squared plus 5 divided by n plus 1, and we're going to say n again is approaching infinity. Okay, so how are we going to do this one? Well, we can see we've got a quotient and we've got a square root here, so we're going to have to use those two properties at least. We've also got adding here, of course. So we're going to have to change this. We're going to have to try and get rid of this square root somehow. Try and bring it out here somehow. Now we can see that the denominator isn't square rooted at all, so what we're going to have to do is square it and square root it. So let's do that. So I'm going to write down this as the limit of n going to infinity of the square root of 4n squared plus 5. And I'm going to put a square root in the bottom here. So I'm going to say that's square root of n plus 1. Now these are two different fractions completely, so I can't do this. So what I'm going to have to do is square this here. If I square this n plus 1 and then square root it, I'm effectively cancelling out the squaring, if you like. So now I have a square root on the top and a square root on the bottom, so that's just simply the limit as n approaches infinity of the square root of 4n squared plus 5 over n plus 1 squared. Now that's just simply, again, I can take, now I have a square root over the entire fraction, so I can take that outside here and write it as the square root of the limit using my root property as n approaches infinity of 4n squared plus 5 over, now I'm going to square this out, I'll get n squared plus 2n plus 1. Okay, so almost there. Now I can work out this limit inside the square root symbol here, so that's just going to be the square root of, now remember I've just got to divide the top and the bottom by the highest power of n, which is n squared. So divide this by n squared, I get 4. Divide this by n squared, I get 5 over n squared. Divide n squared by n squared, I get 1 plus 2 over n when I divide this by n squared, plus 1 over n squared. Okay, now when I work this limit out, then I will end up with the square root of, the limit of 4 is 4, the limit of 5 over n squared, as we saw earlier, is 0, limit of 1 is 1, the limit of 2 over n is 0, the limit of 1 over n squared is 0. So I just simply end up here with the square root of 4, which is 2. So the limit of our function is 2. So if you were to plot that particular function, if you were to draw this particular function here, you'll end up with something like this and something like this, and this horizontal asymptote here, the horizontal asymptote will be at y is equal to 2. Y is equal to 2. So their function will approach y is equal to 2 there.